Hello, welcome back to the Terra devlog, a survival and exploration game set on your very own planet. In the last video, I showed you how I made biomes in Terra using PCG for foliage and the Voxel plugin as my planet's surface. But as I mentioned in the end of that video, I wasn't really happy with the result. Juggling three separate systems, PCG, the Voxel plugin, and my own Terra systems, meant tons of hacky workarounds trying to get them all to communicate with each other, and the performance was nowhere near where I wanted it. And therefore, I ended the video by saying that I wanted to try making my own voxel and foliage system from scratch, designed around Terra, so I would have full control over flexibility and performance. So that is what I've started doing, and in this first episode of making this system, I'm covering how I built a custom mesh component that can efficiently render a marching cube's surface as a chunk, which is the first piece of the system that will eventually become my planet. I'll be going through my full process of building this component from scratch, starting with why I ditched Unreal's built-in procedural mesh component and wrote my own Vertex factory instead, and what that taught me about how the engine communicates with the GPU to render mesh data. Then going from one single triangle on screen up to a full marching cube surface. And finally testing the performance by animating it so it changes and regenerates every single frame. And I've mentioned this marching cubes a couple of times now. So let's just take a quick detour by taking just a high-level look at what marching cubes actually is before we go any further. I'm not going to cover how to implement it, but understanding the concept will make the rest of the video a little bit more understandable. So what is marching cubes? Imagine a big box in your world. Now fill this box with a grid of points, and give all those points a value between 1 and -1 based on a noise function like 3D Perlin noise. This value we call the density. And if this density is greater than 0, make the point green, and if it's less than 0, make the point red. And this is called a 3D density field. And now we want to make a 3D mesh based on this density field, and this is where the marching cubes algorithm comes in. It looks at the density field, and everywhere where the points cross from being green to red, it makes a wall of polygons. And if we do this for all the points in the density field, you get a complete mesh. If we change the density field values, the mesh changes with it. Make the density form a sphere, and you get a spherical mesh. Make it form a mountain, you get a mountain. And this is exactly what makes it so powerful for procedural terrain, and why it's the approach I'm going for in Terra. And marching cubes itself isn't really that hard to implement. There are tons of great tutorials out there. I'll link some of the ones I found the most helpful in the description. And if you just want something up and running quickly, Unreal's built-in procedural mesh component makes it really easy. You run the marching cubes algorithm on your density field and feed the output data into the mesh component, and it just works. That's what I did in this initial testing. But simple almost always comes with a cost, and for me, and usually, that cost is performance. I need this system to handle tons of surface edits happening at the same time, while also keeping the game smooth and still leave enough headroom to build the rest of the game on top of it. And the built-in component doesn't quite get there. I tried animating the density field and regenerating the mesh every tick, and it worked quite well. But as soon as I added a couple more of them, my PC started struggling quite a bit. And in the final planet, I could be dealing with hundreds of these chunks at once, so this clearly isn't the most optimal way to go. And the reason for this is that the built-in component is meant to be general purpose. Every vertex carries tons of data, like UV coordinates, tangents, skinning weights, and more, and for most cases that makes sense, but for my low poly terrain, most of that data is not really needed, and I'm never going to touch it. But the built-in component, of course, doesn't know that, so it has to process and store all of this data anyways, making it far heavier than it needs to be. So I decided to ditch it and build my own from scratch. And there are many benefits to this. I control what data each vertex stores, so I can remove everything I don't need and add anything that is actually useful for my exact case. I control how that data is laid out on the GPU, so I can optimize it as much as I want. and I control exactly when and how data gets sent from the CPU to the GPU and when it actually gets rendered. And because I own the whole system, I don't have to worry about how it connects with some third-party system or plugin I have no control over. But there are of course downsides too, and the downsides are pretty much the same as the benefits. I have to manage everything manually. The Vertex data, the CPU to GPU transfer, all of it. And if something breaks or performs badly, I'm the only one to blame. I can no longer blame any plugin creators, and I can't submit any bug reports and expect someone else to fix it for me in the next update. It's all on me to figure all that stuff out. So, of course, it takes a lot more time, but I also learn a lot more, and hopefully over time this becomes a solid foundation for the whole game, instead of a fragile stack of built-in and third-party systems held together with duct tape. So that's why I think this experiment is going to be worth it. I learned about custom mesh components, scene proxies, vertex factories, render threads, RHI resources, and tons of weird systems and terminologies I had never touched before. And let me break down my understanding of all of it. Basically, there are 3 stages your data has to go through before being rendered on your screen. I call the first stage the define stage. This is where the whole pipeline starts. Directly inside the component itself, you describe what your mesh looks like using regular CPU-side C++ code. And this data is usually regular arrays, which are easy to read and easy to modify. And the next stage is the translate stage. Here, something called a scene proxy takes that CPU-side data and converts it into something the GPU can actually read, called RHI resources. And then it sends those over to the GPU as big blocks of GPU memory, basically. And finally, the render stage. Something called a Vertex factory takes the GPU memory sent by the scene proxy, decodes it into actual Vertex data, and uses a Vertex factory GPU shader to draw your mesh on the screen. So, 3 stages to implement. Define the data, translate the data, and lastly, render the data. If we look back at my initial implementation with a built-in procedural mesh component, we clearly see how much easier it is to work with. Because in here you only have to deal with one of the 3 stages, the define stage. We get the marching cubes output as regular arrays, hand it over to the component, and that's it. The translate and render stages are handled for you automatically. But for my own pipeline, we will have to dig into those 2 as well. And my first goal was simple. Get one single triangle rendering in the world using my own custom pipeline. So I made a component for the triangle, and by following the 3 stages, I see that I first have to enter the define stage. Describe the data needed to render my triangle. And for a triangle, this data is pretty basic. I need an array with 3 points, 1 for each corner, and an array of indices that tells the mesh which points to connect to form the triangle correctly. And that's why the triangle is such a perfect starting point, because it's the most basic polygon we can make and it's super easy to define using regular code. But then we have to enter the second stage, translating the data to something the GPU can understand. This is where we take those simple CPU-side arrays and convert them into RHI resources, which the GPU can read. A tricky part of this is that it has to happen on the rendering thread, not the game thread. And those 2 threads always run completely independent from each other, so you have to be really careful about when and how you move data between them, or it might get corrupted, leading to all sorts of weird bugs and crashes. I won't get too deep into it here, as it could probably be a whole other video, but that's the important part. Once we have those RHI resources and a bit more gray hairs on our head, we can send them over to the Vertex factory and the last render stage. The Vertex factory is the last piece of the pipeline. It takes the RHI resources we made in the last stage and draws the data to your screen. And since drawing stuff to the screen is the GPU's job, that means that the Vertex factory has to run on the GPU, not the CPU like the rest of our code. And that means that the Vertex factory has to be a shader, written in a language called HLSL, not regular C++, which I'm used to. And this complicates things quite a lot, as I have always struggled writing HLSL code. But luckily, I wasn't completely alone. I was able to find some great Vertex factory implementations both in the engine itself and the Voxel plugin, which I could use as examples. But my community has also been really helpful. A special thanks to Trouble in Space, who has also gone through this exact same process for their game, who helped me debug some issues I had with my own implementation. And also, if you're not already a part of that community, feel free to join my Discord server with the invite link in the description. After a long while of crashes and debugging, it finally worked. I got a simple, bare-bones Vertex factory shader up and running, and that meant a single triangle rendering in the world using my own custom pipeline. And it might not seem like a lot, but now, since I can render one triangle, rendering any number of triangles isn't actually that much harder. Since the pipeline is already there, I just have to change the data I feed into it. So, to test that, instead of defining a triangle in the define stage, I shape the data as a cube. All I need is 8 vertices, 1 for each corner, and a set of indices telling the GPU how to connect them. Then, letting this data go through the pipeline, a cube appears instead. No massive amounts of extra work, just different data using the same basic pipeline. Awesome. But this is also where I noticed my pipeline had an issue, because none of my meshes were casting any shadows. And this had me stumped for days. Was there anything wrong with my Vertex factory? I double and triple checked it, but it looked fine. And nothing in my scene proxy seemed to be the cause either. And I also made sure several times that shadow casting was enabled everywhere. I even asked AI to analyze my files to see if it could find any inconsistencies, but it didn't find anything relevant either, just gave me even more issues. So then one day I decided to have a second look at my define stage in the component itself, which I hadn't even bothered to look at since I thought that out of all the 3 stages, this first one I had under control. But it turns out that because I was using a mesh component as the parent class, there were some function overrides that I had missed, and without them, the engine was treating all the materials I applied as transparent, and transparent materials don't cast any shadows. But after overriding those and shaking my head a bit, shadows appeared. So I guess there's some sort of moral in there somewhere, like confidence makes you blind because when you stop questioning something, it will eventually bite you in the ass. I don't know, I figured it out at least, which was very nice. So great! Now with my shadows working, I could move on to the real goal. Rendering a full marching cube surface through my custom pipeline. So I copied the logic from the old example into a new component. In the define stage, I ran my marching cubes algorithm on a density field and got back a result with all I needed. A vertex array, an index array, and a normal array. Then, in the translate stage, my scene proxy translated those arrays into GPU-readable RHI buffers and shipped them over to my Vertex factory shader. Then the render stage takes over, and just like that, a full marching cube surface running through my own custom pipeline. And this feels so much faster than the built-in procedural mesh component. I have my noise function variables exposed in the details panel, and tweaking them in real time feels so nice. It's really fast. So it looks pretty good, but to really test the speed of the system, I want to try to recreate the density field, marching cube surface, and the mesh generation as fast as possible to see how the frame rate holds up. So back in my component, every tick I launch a new request to rebuild the marching cube surface, but with a slight offset applied to the noise function each time, so it should look like the surface is animated. The marching cubes algorithm itself runs on a separate thread, so that shouldn't really affect the frame rate at all. So what we're really testing here is how quickly the mesh generation pipeline can update. So let's click play and see what happens. Wow, that looks really smooth. Let's turn on some stats. And with this one chunk, it looks like we're close to 200 FPS. Let's try it with many chunks. Almost 120 FPS with 16 chunks updating every tick, and already a massive improvement from the 16 FPS we got with the 7 chunks earlier. Nice. That is amazing. Now, of course, it's not perfect yet. The mesh doesn't have any sort of collision, and the noise function is still really basic. So there's probably still a lot of work ahead. But at the same time, I haven't spent a lot of time optimizing the pipeline at all, so we could probably squeeze a bit more performance out of it if we need it. But just having this foundation in place is a massive win for me and will allow me to have much more control over my whole pipeline. The next step now is to try to actually generate my whole planet using this pipeline, which is also a really big task. We will require a chunking system, multiple LODs, and some way of stitching the chunks with different LODs together. So there's still a lot to figure out, but I'll save that for the next episode. For now, I'll spend some time enjoying my animated marching cube surface and be proud of what I've built so far. If you want to be here for the next part, where we use this pipeline to make a full planet, make sure to subscribe. And again, remember to join the Terra Discord server with the invite link in the description to follow the development live, share your own projects and give your inputs on Terra. But that's it for now. I really hope you enjoyed the video, and if you did, a like would bring a big smile to my face. Catch you later!